So the next chapter is pressure. Now, when most people hear the word pressure, they will probably think of something like this. And they are right. That too is pressure. But what exactly is pressure? Well, it's simple, and it's born from the word press. When you press something, we say you're exerting pressure on it. And the amount of this pressure depends on two things. One, the force that you're exerting on the object. And two, the area of the surfaces in contact. Just these two. The ratio of these two is what is pressure. Pressure is force per unit area. Mathematically, pressure is equal to force over area. How about the unit of pressure? It is derived from the units of force and area. Force is given in newtons and area in square meters. So newtons over square meters gives us newtons per square meters. This is the unit of pressure. We also call it Pascal. And so 1 Newton per square meter is equal to 1 Pascal. So, depending on the amount of pressure that we want, we vary these two variables, force and area. If we want a high pressure, we can either increase the force or reduce the area of contact. If we want low pressure, we do the exact opposite. And here is how it works. If we want to drive a nail through a piece of wood, the sharp end of the nail is the one in contact with the wood. Because it is sharp, the area of contact is very, very small. So with just a little force, we can have a very huge pressure on the wood. Imagine if we tried driving the nail through the blunt end. We will need to hit the nail with so much force to drive it in, and I doubt if we will ever be able to do that. And that is because the area of contact between the nail and the wood is large, which reduces the pressure between the two. Now, it's not always that we need high pressure. Footprints on a sandy surface are the result of pressure exerted by our feet on the ground. If you try to walk on a sandy ground with high-heeled shoes, they are going to sink in the sand. Because of the sharp heel, the contact surface area is so small, and that makes the pressure to be very high. This is why large trucks have very many tires, so that their weight can be distributed over a large surface area and thus reduce the pressure on the roads. So these trucks can carry very heavy cargo without damaging the roads or busting the tires. And it's really simple to visualize that. Consider this inflated balloon. If we pressed it on a single pin, it will burst immediately with very little force because the contact area of the pin's tip is very, very small. But if we increased the number of pins, the same force cannot burst the balloon. By increasing the number of pins, we have increased the area of contact and thereby reduced pressure. Now the balloon can take more force without bursting. Solids, liquids and gases all exert pressure on surfaces because, as we shall see, they have weight. Let's start with solids. Consider this box weighing 10 newtons resting on the table. Because it has weight, it's pressing on the table. In other words, it's exerting pressure on the table. How much pressure? It's given by force over area. We already have force, that is the weight of the box. And all we need to do is calculate the area in contact with the table. It will be 4.0 times 1.0, giving us 4 square meters. So pressure is equal to 10 newtons over 4 square meters, and that gives us 2.5 newtons per meter squared, or simply 2.5 Pascal. If we turn the box like this, Now the contact area has reduced. The weight is still the same, but it's pressing down on a smaller area. That is 1.0 times 2.0, which is equal to 2.0 square meters. So pressure is equal to 10 newtons over 2.0 square meters, giving us 5 Pascal. Next, we go to pressure in liquids. Consider this liquid held in a container with 3 holes made at different heights. When the holes are opened, it is noted that the water gushes out and shoots the largest distance from the lowest hole. The water gushes out due to the pressure exerted by the weight of the water above each of the holes. As you go down, the weight of the water over each of the holes increases, meaning increased pressure. Let's see how pressure is expressed in liquids. Consider a beaker containing a liquid of density ρ to a height h. We drop a coin with an area of cross-section A into the beaker. The volume of the water column above the coin, V, is equal to the area of cross-section of the coin times the height of the water column. That is, V is equal to A times H. We call that equation 1. The mass of the liquid column, M, is equal to volume times density. So M is equal to V times ρ. Substituting equation 1 here, then M is equal to AH times ρ. We call that equation 2. Weight of the liquid column is equal to mass times the acceleration due to gravity, g. That is, weight is equal to mg. Substituting equation 2 here, then weight is equal to AH ρ times g. This weight is the force that the liquid column is exerting on the coin. And we know that pressure is equal to force over area. And so P, pressure, is equal to AH ρ g over A. The A cancel out and pressure is equal to H ρ g. This is the expression for the pressure exerted by a liquid of density ρ at depth h. For a given liquid, the density is constant and so is g. For such a liquid, pressure varies with height. For 2 different liquids, the variables are height and density. And so unlike solids, pressure in liquids depends on the height of the liquid column and density of the liquid. The cross-sectional area does not matter. This formula is also used to calculate the pressure due to a column of gas. From our experiment, water gushed out the farthest because this is where pressure was largest. It increases with depth. This explains why dams get thicker and thicker as you go down, in order to withstand the higher and higher pressure as you go down. Let's take an example. A coin of cross-sectional area 12 square centimeters lies at the bottom of a pool, 6.5 meters from the surface. Calculate the pressure due to the water. Now, although we have been given the cross-sectional area of the coin, we know pressure in liquids does not depend on that, so we ignore it. Pressure is equal to H ρ g, 6.5 meters times 1,000 kilograms per cubic meter times 10 newtons per kilogram. That gives us 65,000 Pascal. So let's perform an experiment to confirm that pressure in fluids vary with depth and density. We take a thin sheet of rubber from a rubber balloon and stretch it over the mouth of a thistle funnel. Connect the thistle funnel with the rubber tube to a U-tube mounted on a vertical wooden board with a graduated scale. Fill the U-tube with a colored liquid. We see that the levels of the liquid on both arms are the same. We take a cylinder with water and lower the diesel funnel to a point P inside the cylinder. Record the difference in the liquid columns in the U-tube. This difference is due to the pressure exerted by water at point P. You can calculate that pressure. We then lower the diesel funnel to a point Q, and again note the difference in the levels of the liquid in the U-tube. This difference is due to the pressure exerted by water at point Q. We notice that at point Q, the pressure is higher than at P. So we can conclude that pressure increases with depth. Next, we observe the liquid levels in the U-tube when the diesel funnel is dipped into water, glycerin and alcohol. They are all different, with glycerin being the largest and alcohol the smallest. And that is because the density of glycerin is the largest and that of alcohol is the smallest. Finally, we note the difference in the levels of the liquid column with the diesel funnel pointing vertically downwards, vertically upwards, and towards the sides of the tall cylinder. We notice the difference is the same for all the three, and this shows that pressure in a fluid is the same in all directions at a given depth. Next, we look at transmission of pressure in liquids. Consider water in a flask fitted with an airtight piston and having a number of side tubes at different levels. The level of water in all the side tubes is the same. Now apply some pressure by pushing the piston. The level of the water in all the sides rises through the same height. Water rises through the same height because the pressure applied at one point in a liquid is transmitted equally to every other point in the liquid. This is called Pascal's principle. It states, pressure applied at one point of a liquid in a closed system is transmitted instantaneously to all other points in the liquid. This happens because liquids are incompressible. Let's look at some of the applications of this principle. We start with hydraulic machines. Now, the working of hydraulic devices like hydraulic lift and brakes are based on Pascal's principle. These systems work on multiplying force so that a huge amount of work can be done at another point by applying a small force on one end. An incompressible liquid, generally oil, is used. This is a simple hydraulic system. Two pistons are fitted into two glass cylinders filled with oil and connected to one another with an oil-filled pipe. If you apply a downward force on one of the pistons, then the pressure is transmitted to the second piston through the oil in the pipe. Since oil is incompressible, then no pressure is lost, so most of the applied force appears on the second piston. An advantage of the hydraulic system is that the connecting tube can be of any length or shape. Another advantage is that it can multiply force. This is done by using pistons of different cross-sectional area. Let's see the hydraulic lift. This is a hydraulic lift. The two cylinders have different cross-sectional area. A small force applied on the small piston is multiplied and can lift a heavy load on the larger piston. This is how it multiplies force. Assuming the small piston or cylinder has a cross-sectional area of 0.05 square meters and the larger one has 5 square meters. And suppose we apply a force of 10 newtons on the smaller piston. Let's see how much force will be generated on the other end. So, how much pressure will be generated on the small piston? Pressure is force over area, which gives us 10 over 0.05, giving us 200 Pascal. Now, this is the catch. pressure transmitted through a liquid is not lost. So this 200 Pascal will be transmitted instantaneously to the larger cylinder. So how much force will it generate there? 200 Pascal is equal to force over the area of the larger piston, 5 square meters. So to get force, we multiply 200 times 5, and that gives us 1,000 newtons. You see, applying a force of 10 newtons, we generate 1,000 newtons by simply changing the area of cross-section. So we can lift a very heavy load. The two are related by the formula force 1 over force 2 is equal to area 1 over area 2. Next, hydraulic brakes. Now, the hydraulic brake system consists of a brake pedal, a piston, a master cylinder, 4 hydraulic lines, 4 brake cylinders also called slave cylinders, brake pistons and restoring springs. The master and slave cylinders are connected by a thin copper pipe that we call the hydraulic line. Brake oil is filled in the master cylinder and the slave cylinder and are fitted with airtight pistons. The master cylinder is connected to the brake pedal. The brake cylinder pistons are connected to the brake shoes in each of the wheels. When the brake pedal is pushed down, it pressurizes the brake fluid in the master cylinder, and this pressure is transmitted equally all over up to the slave cylinders. So let's focus on one wheel to understand. When the pedal is pushed down, the pressure in the master cylinder is transmitted all the way to the slave cylinder in the wheel. This pressure causes the pistons to be pushed outwards. This also pushes the brake shoes against the wheel drum, hence causing it to halt its rotation. When the pedal is released, the return spring forces the pistons of the slave cylinder back, and the fluid flows back into the master cylinder. Right, so much for liquids. Let's now talk about air pressure or atmospheric pressure. Now, the atmosphere surrounding us is a deep ocean of air extending for kilometers above the Earth's surface. So we live at the bottom of an ocean of air. And because air has mass, gravity pulls on this mass of air, creating pressure. The pressure is greatest at the bottom. That is the Earth's surface, the level where we live. We call this pressure atmospheric pressure, or pressure due to the weight of the atmosphere. And it is large. At sea level, the atmospheric pressure is about 101.3 kilopascal. That is around 101,300 newtons per meter squared. So, if you have a table 1 square meter in area, the force on that area created by the atmospheric pressure is equivalent to 101,300 newtons. That is equivalent to the weight of 10 cars sitting on the tabletop. If then that is true, why doesn't the table collapse? It turns out that pressure in fluids like air transmits in all directions, not just downwards. This means that the 101,300 Newton force pushing down on the table is balanced by an equal force pushing up. So the forces are balanced. Similarly, our bodies are not crushed because the fluids inside our bodies create an outward pressure that balances this atmospheric pressure. Let's demonstrate this pressure. We fill a glass with water. Cut a small piece of card large enough to cover the top of the glass. Lay the card on the glass. Hold the card in place and rotate the glass upside down. You will see the water stays in the glass. The card provides a rigid boundary between the water and the air in the room. Atmospheric pressure pushes up on the card. Atmospheric pressure is not pushing down on the water, because there is a vacuum at the top of the water. Atmospheric pressure is pushing down on the outside of the glass, but this does not affect the water. The only downward force on the water is its weight, which is easily supported by the upward push of the atmospheric pressure. But if a hole is drilled at the bottom of the glass, air enters, atmospheric pressure will push on the water surface and the water will fall off the glass. Let's do another demonstration to prove the existence of atmospheric pressure. We take a light metallic can and pour some little water inside. Heat the can and its content on a Bunsen burner until the water starts to boil. Put the hot can upside down into cold water. The can collapses. Before the can is heated, it has some water and gas molecules. When the can is heated, the water vaporizes into a gas. The gas fills the can and presses against the sides, creating an increase in pressure, which balances the atmospheric pressure pressing from outside. When placed upside down in cold water, all the water vapor condenses into liquid. This liquid takes a smaller space than the vapor, which reduces the pressure exerted on the can. This means the outward atmospheric pressure is higher than the pressure inside the can. This presses the can inwards, causing it to collapse. And so, going back to our earlier demonstration on liquid pressure, we said that pressure at the hole was due to the weight of the liquid column. But now we are adding something. We now know that the atmosphere is also exerting pressure on the surface of the liquid. So the pressure at any point is equal to the atmospheric pressure plus the pressure due to the column of liquid. Always remember that. Atmospheric pressure is everywhere except in a vacuum. When you use a drinking straw, you are not pulling the liquid up. Once you remove the air in the straw, atmospheric pressure pushes on the liquid surface, causing it to rise up the straw. Consider using a straw to drink water from a glass. It works. Again, using a pin, make 2 holes in another straw and try to drink the water with it. It doesn't work. When you suck up the air in the straw, it means the atmospheric pressure in the straw is reduced since there is no air pushing down on the water. The atmospheric pressure pushing down on the water surface causes the water to rise in the straw due to this imbalance in pressure. In the perforated straw, air sucked up is immediately replaced by another drawn through the holes, so the atmospheric pressure in the straw does not change. It balances with the atmospheric pressure outside on the surface of the water, so the water cannot be pushed up the straw. Consider a series of interconnected tubes of different shapes. When a liquid is poured into one of them, it flows into the others until the liquid stands at the same horizontal level in each of the tubes, even though the areas of cross-section are different. And this is because the pressure acting on the liquid surface is atmospheric pressure and is equal on all surfaces. Similarly, the pressure at the bottom of each tube will be equal since pressure in liquid only depends on depth and density. Atmospheric pressure varies from place to place depending on altitude. At sea level, all the weight of the atmosphere above is pushing on the earth. Therefore, the atmospheric pressure is at its highest. As altitude increases, the total amount of atmosphere above a surface is much less than at sea level. Therefore, the atmospheric pressure is much lower. So atmospheric pressure decreases with increasing altitude. Atmospheric pressure is measured using a device called a mercury barometer. A mercury barometer is made of a long tube closed on the top end and open at the bottom. The tube is filled with mercury, dipped into a pool of mercury, and then raised to a standing position without allowing air inside. The mercury level falls until a balance is reached between the weight of the mercury in the column and the atmospheric pressure against the surface of the mercury pool. The empty space at the top of the tube forms a perfect vacuum. At sea level, the height of the mercury will stand at about 760 millimeters. This is the atmospheric pressure at sea level, 760 millimeters of mercury. As the atmospheric pressure decreases, the height of the mercury in the tube decreases. As the atmospheric pressure increases, the mercury height in the tube increases as well. Next, we look at measurement of pressure, and we start with manometers. A manometer is an instrument used to measure liquid or gas pressure. It consists of a U-shaped tube with a scale and is half filled with a liquid like water. One end of the tube is opened and the other end is attached to a thistle funnel through a flexible tube when measuring liquid pressure. This funnel is covered with a tight, thin rubber skin. When the thistle funnel is outside the water, only atmospheric pressure is acting on it. This is equal to the pressure acting on the open end of the U-tube. And therefore, the water levels on either side of the U-tube remain the same. When dipped into the beaker, the liquid pressure acts on it. The water level in A goes down and in B will go up. The difference in the water level can be read on the scale. This difference is due to the pressure exerted on the thistle funnel. So let's think about this setup carefully. The pressure acting on the thistle funnel is equal to the liquid pressure plus the atmospheric pressure. So how then can we really say that the difference in the height of the water in the U-tube is due to the liquid pressure alone? Well, we must not forget that since the U-tube is open on the B side, the atmospheric pressure is also acting on the surface of the liquid in the manometer. These two atmospheric pressures cancel out. So suppose the difference in height is 10 centimeters and that the liquid is water of density 1000 kilograms per cubic meter. Then the liquid pressure at this depth will be H rho G, 0.1 meters times 1000 kilograms per meter cube times 10 newtons per kilogram, giving us 1000 Pascal. The same instrument can be used to measure gas pressure. We need only to attach the tube to a source of the gas whose pressure we want to measure. In this case, the other end may or may not be closed, and this makes calculation with gas pressure a little tricky. So let's look at that. This is how a manometer will look like when measuring the pressure of a gas trapped in a container. Here, the gas particles will push on the liquid in the tube just the same way the atmospheric gases were pushing. This tube is closed on the other end. It's a closed-end manometer. In this case, the difference in the height of the liquid will be due to the pressure of the gas alone. The empty space is a vacuum, so no atmospheric pressure is exerted on the liquid at this end. Assuming the liquid is mercury, we can calculate the gas pressure because we know the density of mercury is 13,600 kilograms per cubic meter. So at this level, the pressure on the surface of the mercury is the gas pressure, Pg, which we don't know. At the same level on the other end, the pressure is due to the column of the mercury, 26.4 centimeters long. And because they are at the same level, they are equal. So this is also Pg, and this one we can calculate. Pressure is equal to H rho G, 0.264 meters times 13,600 kilograms per cubic meter times 10 newtons per kilogram, That gives us 35,904 Pascal. What if the manometer has an open end? It means the mercury on the right experiences atmospheric pressure on its surface. In this case, the height of the mercury on the two arms will depend on both the pressure of the gas and the atmospheric pressure. Taking atmospheric pressure to be 101,300 Pascal and G to be 10 newtons per kilogram, we can calculate the gas pressure in this example. In this case, the gas pressure must balance the pressure due to the column of the mercury and the atmospheric pressure. So Pg is equal to atmospheric pressure plus H rho G. That is 101,300 Pascal plus 0.137 meters times 13,600 kilograms per cubic meter times 10 newtons per kilogram. That gives us 119,332 Pascal. Next instrument is aneroid barometer. An aneroid barometer is used to measure atmospheric pressure but does not contain any liquid, which makes it easily portable. It consists of a metallic box which is partially evacuated. The top surface of the box is corrugated in the form of a diaphragm. At the middle of the diaphragm, there is a thin rod toothed at its upper end. These teeth fit with those of the circular wheel connected to the pointer. This pointer moves over a scale calibrated with a standard barometer. When the atmospheric pressure increases, it presses the diaphragm and the rod gets depressed. The wheel rotates clockwise and the pointer moves along the scale. When the atmospheric pressure decreases, the diaphragm bulges up, the rod moves up, the wheel rotates, and the pointer moves leftwards, indicating lesser pressure. And finally, pressure gauges. Pressure gauges are portable and are used mostly for measuring gas pressure, tire pressure, pressure of compressed air in compressors, and steam pressure. They are basically made up of coiled, flexible metal tubes which uncoil when pressure inside increases. The movement of the tube is made to drive a pointer across a scale through a combined system of levers and gears. Finally, we look at the applications of pressure in liquids and gases. We start with the bicycle pump. A bicycle pump is an important equipment that does not require electricity. It is made up of a body, a compression chamber, and a hose attached to this chamber and the tire. Inside the body is a piston that moves up and down, compressing air in the chamber and forcing it through the hose into the tire. The piston is connected to a handle. There are also two one-way valves. The inlet valve, which allows air to flow into the chamber but prevents it from flowing out of the chamber. The outlet valve allows air to flow into the hose but prevents it from flowing back into the chamber. When the piston is pulled up, the low pressure in the body draws air inside, which enters the compression chamber because the inlet valve is open. When the piston is pushed down, the inlet valve closes and pressure increases in the compression chamber. The outlet valve opens and air flows into the hose and to the tire. The cycle is repeated until the tire is full. Next, the lift pump. This is a hand-operated device used to pump water. It consists of a lever used as a handle, a piston rod that connects this handle to a piston, which is fitted with an non-return valve. Another return valve is fitted at the base of the cylinder. A pipe is connected to the cylinder and also submerged in water. An outlet is fitted through which water flows out of the pump. When the handle is pushed downwards, the piston is moved vertically upwards. Pressure reduces and the piston valve closes while the base valve opens, allowing water to be drawn into the cylinder. When the handle is pushed upwards, the base valve closes, pressure increases in the cylinder and the piston valve opens. Water is then drawn above the piston. In the next cycle, the piston displaces water through the outlet as shown on your screen. And finally, the siphon. Now, a tube, usually plastic or rubber, can be used to empty tanks or draw petrol from petrol tanks of cars. When used in this way, it is referred to as a siphon. The pressure of the surface of the liquid is atmospheric. The tube is first filled with the liquid and the end C held below the surface. Pressure at C is greater than that at the surface by an amount equal to H rho G. That is, pressure at C is equal to atmospheric pressure plus H rho G. Pressure at A and B is atmospheric pressure since they are at the same horizontal level. The excess pressure H rho G thus causes the liquid to flow out of the tube at C. The liquid will continue to run out so long as the end C is below the liquid surface.